this is the space environment and thermal systems workshop. We're gonna go pretty technical in here. So again, if you guys have any questions, please you feel free to, if you guys want to speak up on mic, just please interrupt me. Or if you want to put it in chat. So is there a way to have chat? Okay, hopefully I pick up chat. It's not popping up, but yeah. So yeah, we'll get right started into here. So again, please feel free to ask questions. I'm sure some of you guys haven't taken heat transfer, so we're gonna dive right into that. All right. So about me, a little bit about me. My name is Arshia Boorboor. I am a mechanical engineering student at UNLV, which is the University of Nevada, Las Vegas. I'm going to be graduating the end of this year in the fall. So, and I am the project lead for RebelSat 1. So I'm mainly on the mechanical side because I am a mechanical engineer, but I help out in all subsystems. So I try to have a basic understanding of the whole CubeSat and try to help the other leads, the other subsystem leads on their design decisions. So yeah. So getting into the content of this workshop, first off, the space environment, very dangerous. Space is extremely horrific. So there's a lot of things you have to consider, especially for spacecrafts. So here's a list of them. There is a vacuum, atomic oxygen, UV radiation, ionizing radiation, plasma, temperature extremes and temperature cycles, and orbital debris. Many of these you don't really have to worry too much because of the mission life of CubeSats. They're pretty small. Typically, CubeSat missions are less than a year. I think pretty sure most CubeSat missions are less than 6 months. So a lot of this you don't have to worry too much, but it's still something that you should at least learn and understand so that you guys know what to expect with your CubeSats. Like I know there's missions that vary, so looking into materials, heat transfer, and all that and other things is definitely important. So first thing we'll go into is the vacuum. So obviously you're in space. It's a vacuum environment. So this causes outgassing. So basically what outgassing is the release of trapped gases inside the materials, inside the solid materials. And they typically on Earth, they want to keep inside. You know, these are very small trapped gases, like in the molecular level. But in space, you don't have that outside pressure. So typically they want to go out of the solid. So this is pretty common in high frequency circuit boards. So this is pretty important. So you want to go into the kinds of materials that anything in your CubeSat is made out of. So this includes electronics. So obviously this can cause, this can render the space electrical equipment useless. So some of these gases can, they could go outwards outside of the solid, and they could deposit on other surfaces of your CubeSat, which could cause problems as well. This is why a lot of materials are on spacecrafts are aluminum, because they don't outgas too much. Specific aluminums, alloys. And then like this doesn't even talk about radiation hitting the bits of your circuit boards. Like going back to the circuit boards, like again, like it could cause a lot of problems, outgassing definitely. These are two resources that I recommend you guys look into. There's the NASA SSP 3426. It's titled the Space Station External Contamination Control Requirements. Now, this one talks a lot about, it was a study of the International Space Station and the materials used of the construction and seeing how it survives in space. So it talks about limits of molecular deposition and induced molecular column densities and the release of particulates because of outgassing. ASTM E1559 is It's titled Standard Test Method of Contamination Outgassing Characteristics of Spacecraft Materials. This is another pretty good resource to have. It's pretty much a database of materials for outgassing properties. So it's a pretty good resource. I recommend you guys look into that. And a lot in this presentation, I'm going to be listing a lot of lists of materials that you could look up for your CubeSats. You could I recommend having a list of all the materials used in your CubeSat and making sure that they comply with standards and making sure that the properties match up and the properties are all good to go. Um, Next after vacuum is atomic oxygen. Now, atomic oxygen is another big thing that you have to look out for. Um, Oxygen still occurs in the upper atmosphere. Like, sure, there's no oxygen for us to breathe, but there's still oxygen up there. There's so much oxygen still that the ISS, for example, still has to consider atmospheric drag because of hitting um, particles like oxygen. So they obviously have to adjust. So there's no excuse for not considering oxygen in LEO. So, and what specifically atomic oxygen is when a short wavelength UV radiation reacts with molecular oxygen. So basically, like the UV radiation hits a molecular oxygen in the upper atmosphere, and this causes some damage, some material degradation to your spacecraft. This is actually the most significant material degradation, in fact, and it can lead to bleaching of materials. Um, there's a model that can estimate how much atomic oxygen fluence for emission, and it's called the mass spectrometer in incoherent scatter model. Um, you don't have to look into that for your specific CubeSats, but it's a pretty good tool that I've researched and I found to estimate that as well. So if you're looking into spacecrafts and designing spacecrafts in the future in your career, I really recommend that tool. The ASTM E2089 is another resource that you could look into regarding atomic oxygen evaluation of the materials for space applications. That one I really recommend as well. It talks basically about materials with atomic oxygen interactions. Specifically, not really, they didn't really test it up in space, but they tested it in a laboratory. So if you're unsure of materials, look like into if you're unsure of the materials and how they react with atomic oxygen, you could look into that. Here's an example of spacecrafts and their kind of interaction with atomic oxygen. I think these are solar arrays of the International Space Station, but you could kind of see like damage right here, and this is caused by atomic oxygen. So definitely something that you should have to look out for things like that. UV and ionizing radiation. Now, this is another important thing to look into. Is another important thing that you have to look into. UV and ionizing radiation. It basically it darkens the materials and damages polymers by either cross-linking, which hardens the material, and then also it also weakens the material by chain scissoring. So this is like this is the type of radiation that electrical engineers look into a lot because this is the one that really damages their electrical components. Um, it creates oxygen vacancies in oxides. So if you have a specific oxide on your CubeSat or any spacecrafts, this is something that you have to look into. Also, it causes electronic event bit errors. So again, this is the type of radiation that electrical engineers look into. So um, I recommend placing shielding for your electrical components to make sure they don't cause any damage or event bit errors and things like that, or using radiation hardened electronics that would help as well. This is an example or a picture of a component in space that was exposed to that UV and ionizing radiation. As you can see on the left, that's a pre-flight. On the right is the post-flight when it came back down. So obviously you could see just the visual damage, but molecularly it did a lot of degradation. So over time, the surface finishes would degrade and it would eventually lose the protection for the components. So again, another thing to look into. And then plasma. Plasma is another big thing to look into. In low Earth orbit, there are positively charged oxygen ions and electrons up in space, just floating around. So, because again, there's oxygen still up there, even though it's like very little, there's still oxygen up there. Because of the velocity of the spacecraft, like moving in orbit, it's going super fast. It's going super fast. So, it could build up a lot of negatively charged ions on the surface of the spacecraft. Um, and it, it would pretty much, there would be deposits of those positively charged oxygen ions and electrons. Um, and this overall affects high voltage solar arrays and conductive coatings. So, um, again, another thing to look out for when designing some spacecraft, especially CubeSats. So, and if you guys don't know what conductive coatings are, they're coatings that like bleed off static charge on the spacecraft. And when plasma hits those conductive coatings, it would just remove the effectiveness of those conductive coatings. So, again, another thing to look out for. So, by the way, does anyone have any questions regarding any of the material that I've mentioned? Okay, no questions. Sweet. So, orbital debris. Again, this is a topic that I'm sure everyone knows about. Um, so they could be traveling super fast as 60 kilometers per second. And they could be as small as like 1 nanometer in diameter. So it's very small, but that could cause a lot of damage, especially the CubeSats because of how small they are. And they can cause short circuits on solar arrays, damage to spacecraft. So orbital debris is definitely not a strange topic. It definitely exists, but um, there's a lot of tools out there that take care of all of that stuff. Not take care, but at least track all that stuff. I know the U.S.
Hello.
government has. Hello, hi there. Do you have a question?
Oh, sorry. I didn't know my mic was on and I got a phone call.
Oh, no problem, no problem. Yeah, so orbital debris again, like super important to take care of. There are tools out there that kind of tracks orbital debris. Sadly, that's not very public knowledge. Like you can't just find on the internet to find a tool that tracks all the orbital debris. I'm pretty sure you need like US government approval to use that tools like that. um I'm assuming everyone here is from the US. So um yeah, so those are that kind of stuff that you have to kind of ask permission for, but still definitely something to look out for. Finally, uh, the big thing is temperature extremes. So as your spacecraft, moves around the Earth, it goes in and out of sunlight, and especially that we don't have that the atmosphere to protect from a lot of that radiation. uh, it's going to go through very high temperature extremes, very high. And so you have to account for this. So thermal cycling temperature extremes depend on multiple factors. Um, One of these factors is thermal optical properties, such as, heat conduction, solar absorptance, thermal emittance, and much more. So um, other Other dependents are view of the sun and the earth, view of other spacecrafts, duration in the sunlight and in the shadow of the earth, thermal mass, heat producing equipment such as the onboard computers. So these are all things that you have to, look after, to really engineer your way through it. And a rule of thumb is to have the overall CubeSat to go through like a 120 degrees C to 120. Sorry, a negative 120 degrees C to positive 120 degrees C. Now that does sound kind of high, or kind of pretty high extremes, but I recommend maybe a little bit like 110 on each side, plus or minus 110, or plus or minus 100. So that's me personally. That's a little bit more on the safe side. There's been arguments on both sides, but that's what kind of like industry standard, pretty much 120. Um, Obviously, temperature extremes are important because they cause thermal deformations. Now, deformations. So for Rebelsat, we had a mission where we would study the thermal deformations of a material um, before we changed that mission. That was one of our mission concepts, and thermal deformations, they cause a lot of protective coatings to degrade, like cracking and peeling and such. So that's something you have to look into for temperature. I would say temperature is like the most important that you have to look into as being on the mechanical team. So looking into, I'm gonna show you how to look into the temperature extremes and how to avoid them, as that's kind of the most important for, especially for CubeSats as well. So small sat thermal control system. So again, this is a mechanical team's responsibility to make sure the electronics survive. And again, the objective here is to make sure the spacecraft components are within the temperature range. So you have to look at all of your electrical components to see what their operating temperature range is and their survival temperature range. There's two different, and I'm pretty sure your manufacturer of the components will they'll provide both. They'll provide both. Now heat transfer again is pretty. It's a whole different field, pretty much in mechanical engineering. Um, there's three different types: conduction, convection, and radiation. With spacecrafts, there's no convection. There's because you're in that thermal vacuum environment, but there's still conduction and there's still radiation. Radiation is the most important. Now, there's two different types of radiation. There is heat transfer between components, which is sorry, internal radiation is heat transfer between components. Um, so the radiation that, let's say, the structure of the CubeSat emits to other parts of the other components of the CubeSat. And then you have external radiation, which is the energy absorbed from the sun or the earth and emitted by the spacecraft towards the cold space. So you could imagine the CubeSat, right? It's absorbing radiation just naturally from the sun and the earth, from the earth because the radiation kind of bounces off of the earth. And then the radiation also gets emitted by the spacecraft towards the cold space. So those are two different types of radiation that you have to look into. I recommend doing this for your CubeSat is having a list of components and listing the operating range and the survival range. Now, this is an example from MIT's Castor nanosat. They listed an operating range and a survival range. If you guys don't know what the difference between those two, operating range is a more strict range. Operating range is a more strict range that must be maintained to achieve the intended performance of that component, while the survival range is less strict, but it's meant for a non-operating phase, and it provides a maximum and minimum temperatures that component can withstand before it renders inoperable. So I really recommend going through each of the components that you have. I'm sure your manufacturer will give those values to you, the operating range and the survival range, and making sure that you analyze through each of these components and making sure that they survive in their operating range. I'm sure that, like for example, batteries, they're going to be under 24/7 operation. Same with solar cells and things like that, and things like camera, maybe your payload. Those things they could fall within that survival range because they're not going to be operating all the time. But again, these are just all things that you have to consider. Again, anyone have any questions about anything? Okay, sweet. Sounds good. Um, so thermal properties of materials. Now, I would recommend having a document of all the materials you used on your CubeSat and make notes. Make notes of the operating range, survival range. Sorry, disregard that. Make notes of the materials used on the CubeSat and kind of going through those documents that I showed previously and making sure that they have good outgassing properties, good thermal properties, optical properties. So yeah, heat transfer is heavily dependent on two different material properties: thermal and optical. Thermal properties of materials is basically how the material conducts heat. Um, there's two different ways to control heat transfer. It's passive thermal control and active thermal control. Passive thermal control is basically having a proper material selection. So making sure the materials have good properties pretty much to withstand that space environment. Active thermal control is where you engineer a way to it is where you engineer your way towards making sure that the thermals are in control. So this is either making heat sinks, making radiators, things like that. Um, I really recommend going through the Spacecraft Thermal Control Handbook. Now, this is a handbook that the Aerospace Corporation made. Very popular resource in the aerospace community, I feel like. They go into a lot. It's basically a book of materials best used for space applications, specifically in heat transfer. So I actually really like that book. It's very useful. I have it on PDF, so I really recommend that book. It's really intriguing. Um, so you have thermal properties, and now you have optical properties. Optical properties is something that not many people know about, yet they're the most important. I would say about 30% of heat transfer for spacecrafts are conduction, and about 70% is radiation. Um, Before I mentioned thermal properties, and those are how materials conducts heat. Optical properties of materials are is how the material radiates heat, so radiation. So this is why optical properties are more important than thermal properties, just because there's much more radiation heat transfer happening on your spacecraft up in space. Highly dependent. The optical properties are highly dependent on surface finishes. So this is part of the reason why NASA asked to anodize all their surfaces. So looking into of the emissivity and absorptivity of materials is the best way to control uh, thermal optical values. But it's kind of difficult to find constant emissivity absorptivity because it just depends on so many different things. So I recommend this resource that's called Solar Absorptance and Thermal Emittance of Some Common Spacecraft Thermal Control Coatings. It's a long name, but that's the name of the document. I'll actually here. I'll post it in the chat. It's a pretty old document. There might be some new materials that they recently studied that are much better with heat transfer and withstanding the radiation. But still a pretty good resource. Um, Again, physics doesn't matter, but it's a really good resource to looking at like what types of coatings are good for your CubeSat, especially the structure. Um, so let's see here. Any questions, by the way, about anything? One example I wanted to bring up as well, um, regarding surface finishes is solar panels. Solar panels, they always point towards the sun. The sun yet generates so much heat, and it could destroy the solar panel. So you might wonder, like, how do spacecraft withstand that heat, that radiation? Most people, they put specifically Z93, I believe that's what it's called, Z93 white paint on the back of the array. Um, that's kind of the best way to have, that passive thermal control for solar panels. Others use multi-layer insulation. Multi-layer insulation is basically like it's a type of insulation, physical insulation that you wrap around the electronics. Though there are many arguments against using these from my experience because um I don't know, it just seems like a lot of people think it's like, oh, it's like it's similar to putting duct tape on a spacecraft. And normally you wouldn't want to put duct tape on a spacecraft, right? But but yet some people say, oh, multi-layer insulation's good and stuff like that. But I don't know. I guess it's your guys' decision to make for your guys' CubeSats. Um, I personally have yet to really look into that too much. Just because I've heard more people say that multi-layer insulation is kind of bad, but I don't know. You guys pick your poison, I guess. So, adaptive thermal modeling architecture. Now, this is kind of like an outline of how you guys should do your thermal modeling. Again, mechanical team's gonna look into this a lot. It's basically like a thermal modeling tool for small sats. It's I really recommend it. This is kind of the engineering that I'm gonna go through for my CubeSat after doing a couple research and development on that. So there's three phases in this thermal modeling architecture. You have the development and verification, validation, and you have implementation. Um, Now, a good tool that kind of adapts this architecture is the adaptive thermal modeling tool. So this is a MATLAB thermal modeling program developed at MIT by John Richmond. And after reading through his paper, I'm going to be adapting some of his ways in doing thermal modeling for small sats. There are other tools other than adaptive thermal modeling tool. You could make like a lot of companies they use custom ones. I'm sure they instead of finding one from the internet. But it's important to have one for validation, which we'll talk about later. So this is what the adaptive thermal modeling tool looks like. You import your geometry, you put your factors in, your conductance, your materials, and you simulate, and then they give you an output. So this tool, after looking into it, it seems really helpful. And again, it's gonna help you verify a lot of things when you do a lot of thermal modeling. So I really recommend looking into this and looking how it works. Now, this is a little bit more put together program, but when you do your thermal analysis for your CubeSat, you would want to do like a MATLAB script and putting in your geometry, putting in your data to verify your results. So this is kind of an outline of the adaptive thermal modeling architecture. Here you have your development and verification. So you have two different, you have the industry standard modeling tool. This could be either Thermal Desktop, ANSYS Ice Pack. There's other tools out there as well to do your thermal modeling. And then you have your adaptive thermal modeling tool, which that one is the one that that I'm kind of choosing, but there are other custom MATLAB codes and scripts that you guys could find or even make on yourself. But you always want to have two. You always want to have two, and this is for everything. This is for whether you're simulating for vibrations, any kind of simulation. You would always want to have two different, and I recommend having an industry tool or a custom MATLAB script or whatever, so that you can verify. So it's going to output those prediction models for each the industry tool and the adaptive thermal modeling tool. And then you compare the two. Now, this is the validation stage. I'll talk a little bit about this in the next slide, but you have the modeling correction and then the modeling data correlation. Sorry, not correction, correlation, model correlation and model data correlation. The model data has another thing called the thermal test data, which I'll go into much later. And then you implement. This is where you look into the results and make your engineering design decisions. And then you do iterations. So as you see, iterative trade studies, you find the results. If they're not performing the way that you want, you go back, make new models, update in the model, and you just do the cycle over and over again until you have the results that you like. So the first step is the development and verification. Now this is you define your on-orbit scenario, and this on-orbit scenario is used to predict your results. These on-orbit scenario characteristics are things like the semi-major axis, eccentricity, inclination, longitude of ascending node, argument of parapsis, and true anomaly. These are all things that you would input into your thermal model. Usually, you would get these from your ADCS or comms team. They would usually have these figured out by now. And then these are used to generate the predicted results and output the predicted results. And then usually, well, these predicted results comes from your thermal modeling tool and your commercial tools, whatever. Next is the validation stage. Now, the validation stage is where you compare the two. You compare it from the commercial tool, your industry tool, to the tool that you've made in-house or whatever. So again, you always want to do something like this when doing simulations, having two types to validate. There's two types of validation that you must go through. One is the model to model correlation. So again, that's comparing your modeling tool results to the industry standard tool results and making sure those are correct. After that, once you do that, you do your model data correlation. So this is, again, let me go back here. This is this. So you have that model to model correlation and then your model to data correlation. And this is where the thermal test data comes in. So what that thermal test data is comparing the prediction model, which is what you simulated, into actual test data. Now, this actual test data is going to be your thermal vacuum bakeout test, for example. I guess an example that I could go into is that thermal vacuum bakeout test. You would want to start out with a simple test case to minimize those unknown parameters, because there are going to be unknown parameters. And usually, obviously, you would want to minimize these unknowns because it could lead to model errors. But overall, you have known parameters and unknown parameters. And the known parameters shouldn't be altered in the model. So these are the dimensions of your model, your geometry, material properties, ambient temperature. These all should be constant. And then your unknown parameters are alternating parameters. And these consist of like surface emissivity, contact strength, absorptance, things like that. And you usually want to alter these because typically you would find data of the alterations, or you could just put like a plus or minus 10% of a constant value, for example, and vary those. Next, after validation, once you compare those two, once you go through the model to model correlation validation and then model to data correlation, you would go into implementation. Now, implementation is where once you verify that all of your data matches up from all these different tools and testing and such, you get the most accurate data set to determine your engineering design decision. So this is where you look at the data, you analyze, and you're kind of seeing what they do, how the thermal modeling is performing. And if they're performing good, then you're good. You don't have to do anything. But again, if it's not in the operating range, then you would need to do some engineering, further engineering, which is doing active cooling or passive cooling. Again, active cooling is where you make some heat sinks, you make some radiators, or you do passive cooling, which is trying to find better materials, better coatings, for example, to use. Um, does anyone have any other questions regarding because this is pretty important when going through and doing your thermal modeling. I hope you guys are making notes. If not, YouTube video is gonna be out. I am recording this, right? Yeah. Okay, I am recording this, so you guys can always go back into this. So, yeah. No, no questions. Dang. Okay. I was hoping for a lot of questions, but okay. But really that's really it. This is really the conclusion. It's just looking into a lot of let me go back here. So I want to reiterate here. Just again going through this architecture of comparing this, just making models using the industry tool. I really recommend Thermo Desktop. It seems like Thermo Desktop has a lot of integration with orbiting spacecrafts. And then also having your own modeling tool, whether that's a different modeling tool that you find on the internet or one that you made. And then during the validation stage, you would compare those two results, making sure that's correct. And then also on top of that, you have to get your testing data in a similar simulation, or not simulation, in a similar environment as space, getting that data, making sure that matches up to your model. And then in the implementation, you would look into these results and making sure you make those design decisions correct. So again, in conclusion, thermal modeling software that I recommend is Thermo Desktop. They do some really good FEA heat transfer on that. If you guys don't know what FEA is, it's a finite element analysis. It's pretty much like doing nodal analysis if you've done heat transfer. But yeah, Thermal Desktop does a lot of satellite thermal modeling, stuff like that. This is a picture of the software actually. This is the ISS. They they're doing a lot of thermal analysis on, so it looks like the solar panels are pretty hot. They're pretty hot. But then the rest of the satellite's pretty cool because they have the passive cooling of the different materials that they have. And they've done a lot. Obviously, ISS has been up in space for a very long time. They've done a lot of studies, a lot on the materials that they used. So it's very important to research these materials that you're going to be using in your CubeSats and making sure that they are all good. So yeah, this is very exciting stuff. At least for me, I'm really excited. Thermals is pretty much one of my favorite things to do, thermal simulations, because it's really exciting because this is real engineering work at the university level, and it's really good stuff. So you'll learn a lot as you guys go through your CubeSat projects and do a lot of this thermal modeling, because this is a real engineering work. Um, Going through references, these are two different resources that I really recommend going through. I pretty much like did a summary on both of these things, but if you guys want even more detail, I'll link both of those in the chat. So you guys could bookmark these, read up on it. The second link that I'm about to send right now, it's pretty long. It's a paper that's like almost 200 pages. But it talks a lot about that adaptive thermal modeling architecture that I talked about here. So again, I really recommend going through this architecture, going through this way of doing thermal modeling and stuff like that. So I kind of scheduled a lot of time to do questions for the last 10 minutes, 15 minutes, which is right where we are. So if you guys have any questions, please ask.
I might just sprinkle in a couple sort of words of wisdom just to kind of tack on.
Yeah.
Like definitely like the thermal aspects, right, of the space environment are going to be a big deal when you're doing like an in-depth design of the satellite. But it's very important to keep it in mind like from the very beginning too, because like the thermal performance of your electronics really can make or break a mission, right? Like solar panels, right? They perform better or worse, right? Depending on the temperature and like you mentioned during the flight computer workshop, right? Like cameras and like sensors, if they're too hot, a lot of times it introduces a lot of noise that can pollute your data if you're collecting data like that. And probably the biggest one that kills a whole lot of CubeSats is, batteries get too cold, they freeze, and mission's over, right? Because like,
You got a brick at that
you
point.
know,
A floating.
yeah, you had a nice brick in space. So yeah, there's a lot of stuff you got to take into consideration. And I know that y'all don't have to worry about it so much in the scope of this hackathon, but when it comes time to actually launch, your launch provider is going to want to know pretty much every single material that has gone into the satellite just to make sure that none of them are going to cause any problems with outgassing. And so that's something that sometimes can actually be pretty hard to figure out, because a lot of times the outgassing data, if it's not like in one of the databases, manufacturers for like things here on Earth, like you don't care about outgassing. That's something that isn't really a problem for most consumer products. I remember for BroncoSat, we spent like a week trying to find the right type of glue, right, to use in the satellite, a proper, low outgassing glue.
Yeah, we have plenty of space glue up here if you ever need any.
I don't top of my head.
Plenty in our workspace.
Yeah, I think it's like the gray stuff, right? Like the
Yep.
Yeah, it's like 3261 or something like that. I don't remember exactly.
Yeah, space is. I feel like space is a whole new world out there. Pretty much, like you have to find the right materials, and that's really kind of the whole point in one of the in these mechanical properties, or a lot of these mechanical workshops, such as the structures one, is material choice. Material choice is very important. Pretty much anything you put up in space has to be analyzed. So
yeah, there's a lot of due diligence you have to do, and Arshia touched on it briefly, but like the orbital debris side of it's like really important too.
Yep.
Right?
Exactly. Yeah.
Yeah, especially if you get into like sort of like the whole like Kepler syndrome concerns and all that kind of stuff, and also like re-entry is a big deal too, right? Like if you're gonna put titanium on that satellite, you're gonna have to justify it really well, because they don't want like those high temperature metals not burning up on re-entry and then causing problems.
Yeah. No. Exactly.
Yeah.
Cool. I mean, if there's no questions, I'm quite surprised, to be honest, because I thought this was going to be a little bit complicated, but I hope my kind of presentation was good and simple and easy to understand. So again, if you guys have any questions, I'll link my email in there. So if you guys want to email me, if you guys are having problems with your guys' CubeSat, I would love to help you guys with thermal modeling if you guys need any help with that. So put my email in the chat, or in the chat. So yeah, think we're good, I would say. Shorter presentation, I would say, but yeah.
Yeah.
Cool. Yeah, go ahead.
Oh, no, I was just gonna ask if like any of the folks still hanging around, like you guys have any general questions just about like hackathon in general, or just CubeSats in general. Like we have time in the slot still, so
I can't say my questions are about the hackathon in general, but I am curious as to why you need like specific government access to deal with tools for orbital debris.
Well, so are you talking about like the ODAR thing?
Yeah.
So yeah, you can get it. You just have to like, there's some small check that they do, and you have to make sure you fill out the form completely. Like I know I've failed a couple times. Like they sent me an email. They're like, oh, like you didn't use like some wrong, like you like forgot your middle name or something that was like stupid. But like you can definitely download it. It's like open source and they're like software.nasa.gov.
Okay.
Yeah, like I think the DAS software, like the debris analysis software from NASA. I don't think there are
That's it.
particular export controls on it. Like, I think it's just kind of rolled into like the fact that it's probably what it is it's built on libraries that are like also used by the government to fly the missiles or something, right? So there's probably some stuff with that. You'll find a lot of this stuff in the aerospace industry, at least the legacy aerospace industry, is tied up in a whole lot of like legal weirdness.
Yeah, no, and anything you really put in space, it's there's a lot of regulation. They really try to put a lot of rules into it, and
Yeah.
it's a reason. There,
Yeah.
you have to make sure that it's not a missile. There's
Yeah,
a fine line between space and military, for example. So
yeah, and there's an element of it too. We don't have a dedicated licensing workshop this year, but like, one of the things you have to do, right, when you launch a satellite, other than get the FCC license, is you also have to register with NORAD. I think it's the 25th Space Wing. Like you have to register your satellite so they can properly track it and make sure it's not gonna collide with any other satellites.
just oh yeah, this is the debris assessment software.
So you can just like, if you scroll up a little bit, you can like in the upper right, you can like, you go to log in, you can like make an account with just like your school email or something. And then when you request it, you have to like fill some stuff out. Oh, here's the thing. You have to do it for like personal use. If you say you're doing it for school, they want to check that you're like a department head or something. So either you have to get the department head to sign on or just do it for personal use. That was what I was saying.
Yeah, like when we had to get our copy of DAS software, like we trying to go like, oh, I am a student's route, like education license. It's like, oh, can you get your dean to send us a letter, right, to verify your school? But if you just say, oh yeah, no, I'm using it personally, then bing bang boom, you get the link like a couple minutes later. Yeah, so to answer Victor's question, we are going to be kind of rolling out like more of a schedule, as well as what the prompt's going to be, right, for the actual hackathon this weekend. We're going to be having 2 industry judges come in, and really what we're headed towards is we're keeping like on theme with the hackathon. The sort of founding principle was, hey, let's design a minimum viable CubeSat mission and get that all together. But if folks want to do something just CubeSat adjacent, like a ground station, like we're totally open to that too. More details to come later tonight, maybe tomorrow morning, depending on when we decide to add people. Yeah, so Arshia's on the Space Track website here. Oh wait, this is Flynn. Never mind.
Yeah, this is Flynn. I was like, wait,
sorry.
what happened?
Oh yeah, no.
Because I have an account already. But yeah, pretty much like there's this catalog of all the satellites, and yours will be one of them. And there's like an API, so you can like go and like request all these just to see where everyone is. Fun stuff. It's free. Sign up.
Yeah, I guess if no one has any questions, I think we're good to go.
Yeah, we just close out for now.
Yep.
Keep an eye out. Tomorrow is Thursday, so we're probably actually going to slap together some kind of impromptu like social event tomorrow night, just to have an opportunity to chat with people. I know I see a lot of familiar names jumping between all the workshops, but haven't actually I haven't actually gotten a chance to actually meet a lot of you people. So yeah, just keep an eye out, and looking forward to seeing you guys throughout the rest of the week, and hopefully seeing some really cool things built over the weekend.
Yes, sir. Yeah, I hope everyone's having a good. Hackathon week. Going through these workshops. I hope you guys are learning a lot. So, thank you, Luke. All right, I think
All
we're
right.
good.
Well, thank you again, everyone. Have a good night. Catch y'all later.
See you, everyone.